Hello everyone, welcome to online session of lasers. Today I am going to discuss the following topics of laser: properties of laser, basics of laser production, expression for energy density in terms of Einstein's coefficients, condition for lasing action and requisites of laser, construction and working of carbon dioxide laser. And these topics that will be covered in the study material from the page number 1 to 10. So let us see what is laser and their characteristics. Laser is the acronym of light amplification by stimulated emission of radiations. So as the name suggests, that the light amplification that can be achieved with the concept of stimulated emission process, that is how lasers can be produced. A laser beam is highly parallel coherent beam of light of very high intensity. A lasing action can be achieved by creating the population inversions. We will see in detail what is population inversion, pumping, etc., etc. And this population inversion, which can be achieved by different means such as optical pumping, electrical pumping, solar energy, etc. Now the characteristics of the laser beam are they are monochromatic, coherent, highly directional and high intensity. So first let me take of monochromatic laser beam. So monochromaticity in the sense the laser beam which comes out from the source has got single color. So single color correspondingly single wavelength, which means the light which is having a single wavelength are called monochromatic light or the monochromatic beam. Now this monochromaticity, because of the highly coherence property of the light source. Next concept is the coherence. Coherence is the another characteristics of the laser beam, which is the most important optical property which distinguishes the laser light from other types of the monochromatic light. There are two types of coherence, namely temporal coherence and spatial coherence. So let us see what are temporal coherence and spatial coherence, and when it occurs, these two types of coherences. So temporal coherence, it occurs normally the wavelength of the light radiations emitted by any monochromatic sources have a certain variation in their wavelength. In other words, there is no light waves of the source is ideally monochromatic, which means there is a small variation in the wavelengths of the emitted light from the source. So if the difference in wavelength between the different waves is small, then the temporal coherence of the light is said to be high. Is that clear? If the difference in the wavelength of the light waves is less, then the temporal coherence of the light is said to be high. The laser light is highly monochromatic. It has a high temporal coherence. Since it is a highly monochromatic, it has high temporal coherence. Right. Next is spatial coherence. At any given point of time, if the phase difference between any two points separated spatially in a wave, that is equal to phase difference between any two points which have same spatial separation in any of the waves emitted by the same source, then the light is said to be spatial coherence. So in other words, in terms of the phase difference, that is what the spatial coherence in the sense. So in the first point we are talking about the wavelength difference, and the second point the spatial coherence that will gives the information about the phase difference of the light waves. Next characteristic is directional. So as I explained the monochromaticity as well as the directionality, let me take an example. The conventional source, say sodium vapor lamp or the mercury lamp, they are all non-chromatic and it is not directional. Why? Because it spreads the light waves in all directions. So obviously the intensity of the light wave is going to diminish. So obviously it is not highly directional. When it comes to the laser beam, it is not so. Here all the energies or the all the photons which are concentrated in such a small region, therefore the energy is high, that energy can travel for a longer distance without diminishing in intensity. That's why the laser light is highly directional one, and it has got high intensity too. The intensity of the laser beam, that's because of the phase correlation that exists continuously between the photons issued from the laser sources. That's quite obvious. In a laser beam there is so many photons, they have a zero phase difference, so because of that it has got high intensity. The laser light is highly intense, and intensity is too high when compared to the other light sources. Now, for instance, let us compare the what way the intensity of the laser light is very high. So, light from the laser source of something like a helium neon laser. That means a laser light comes out from the helium neon laser, which is hundreds of times more intense than that of the light starting from an equal area of the surface of the sun. That's what the informations you can think of. So these are the characteristic features of the laser beam. Please remember the characteristic features of the laser beam are the monochromatic, coherence, directional and highly intense one. Now next we'll see the basic principles involved in the production of the laser. So production of the laser light is a particular consequence of interaction of radiation with the matter. The interpretations of the interactions is done on the basis of ideas related to the energy levels of the concerned system from which the light is derived. So for the generation or the production of the laser, there is a concept called the matter and radiation interactions. That is must. So for any matter, whether it is characterized by energy bands or by discrete energy levels, the energy quantization rules always holds good. Hence for matters, irrespective of its state of existence, is referred to as an quantum system or quantized systems. So now let us see what are the basic principles involved in the production of the laser. So when radiation interacts with the matter under appropriate conditions, the interaction leads to an abrupt transition of the quantum system, such as an atom or a molecule from one energy state to the another one. If the transition is from a higher state to a lower one, the system gives out a part of its energy, and if the transition is in the reverse direction, then its absorption of the incident energy. So this is what the basic principle. Please think of, when a radiation interacts with the matter, there are two things are happening. One is abrupt transitions. It may be from lower energy state to higher energy state, or higher energy to lower energy state. Either way, there is a liberation of some sort of radiation in terms of energy. Alright, in order to understand the manner in which radiation can interact with the matter, consider two energy states, say E1 and E2 of the system, that you can see the slide. Now the system may be a collection of atom or molecules. If the energy difference between the two energy levels is delta E, that means E2 difference E1, that is equal to delta E. Then according to the Max Planck's an electromagnetic radiation whose frequency nu is given as this difference in the energy by h. This equation is written by using E equal to h nu equations. Nu is equal to E by h, where E is nothing but the change in the energy, therefore delta E by h. So this frequency of radiation is incident on the system which is in the energy state E1. Then the system can move to the energy state E2. Please remember, system is, it's a collection of atoms or the molecules. Now once the radiation is made to incident onto this particular system, they will absorb the energy, they will move to the energy state E2 by absorbing the energies. Alright. On the other hand, if the system of the state which is in E2 state, which emits a radiation of frequency nu when it transits to ground state, that is E1 state. So either way, there is a radiation with either absorption or emission. So the frequency of the radiation emitted is nu, that is equal to delta E by h. So there are three possible ways through which interaction of radiation and matter can take place. One is the absorption of radiation, other one is the emission radiation. These emission are of two types, spontaneous emission and stimulated emission. So there are three different interactions are possible when matter interacts with the radiations. What are those interactions? There are induced absorption, the spontaneous emission and stimulated emissions. So let us see one by one what is induced absorption, spontaneous emission and stimulated emission. Alright, let me take up induced absorption. So induced absorption means it is the absorption of incident photon. Please remember, it is a absorption of incident photon by a system, as a result of which the system is elevated from lower energy state to higher energy state, wherein the difference in the energy of the two states is precisely the energy of the photon. Please see the slide. The energy state E1 and E2 is given a photon of h nu, that's the energy of the photon, that is given to the atom which is located in the ground state or E1 state, so that the atom takes the energy, absorbs that energy, then goes to the higher energy state. The transition is completed. So this state of the transition can be represented as atom plus photon, that will give rise to atom star, where atom star is nothing but atom which is in the excited state. So energy difference in the higher energy state to the lower energy state is delta E, that is nothing but E2 minus E1. Next, spontaneous emission. Spontaneous emission is the emission of a photon when a system transits from higher energy state to a lower energy state without the aid of an external agency. So please remember, this is the process of emission wherein there is no role of the external agency. Without the aid of an external agency, atom will undergo the downward transition from higher energy state to the lower energy state. So you can see the slide, the energy level representation is shown in the picture. Now to explain the spontaneous emission, let me consider an atom in an excited state, exactly shown in the slide. Because of the universal tendency that an atom which is in the highest energy state, that will stay at that higher energy state for a very short time duration. Thereafter, voluntarily it will undergo the downward transitions with the emission of a photon. Therefore, the energy difference again is delta E, that is E2 minus E1, when it undergo downward transition from E2 to E1. Therefore, the state of a system is represented as atom star is equal to atom plus photon. So please remember, without the aid of any external agency, the photon is liberated and atom came back to the ground state. This process is called the spontaneous emission. That's why the word spontaneous. Spontaneously, immediately, after a very short duration, the atom after attaining to the higher energy state, it will come back to the ground state. The photon may be emitted in this process of any direction. That means the direction of the emitted photon is not same. Say for example, if the two such photons which are spontaneously emitted by two atoms under the identical conditions may not have any phase differences or phase similarities. They may not have the phase similarities, and even they may not have the same direction. So that is the reason why these photons are incoherent. They are not coherent. In the sense, there is a phase difference existing these photons. So this is the kind of the emission that occurs in a glowing of electric bulb or a candle flame. Next discussion is stimulated emission. So here it's a very important topic as far as the production of the laser is concerned. Stimulated emission is the emission of a photon by a system under the influence of a photon passing just right energy due to the system transits from higher energy state to the lower energy state. The photon thus emitted is called the stimulated photon and will have same phase and energy, also the direction of movement as that of the incident photon. So you can see the picture here, the higher energy state and lower energy state, and before incidence there is one photon, that's the incident photon actually, an atom which is in the higher energy state. In the previous case I explained that it voluntarily comes down. Now before coming to the voluntarily transition, one photon should be incident. It is vicinity of the atom which is at the higher energy state. By that time what happens? The atom undergo downward transition with the liberation of a photon. Now the incident photon and the liberated photon. So these two are emitting at a time, and these two photons having same phase difference, same energy, and also the direction of propagation. That's why these photons are coherent, and these coherent beams are, or the coherent lights are very important in the production of the laser light. And the process is represented in terms of atom star plus photon is equal to atom plus 2 photon. That's quite obvious. Atom in the excited state, again one more photon is just sent near to the atom which is in the higher energy state. As a result, 2 photons are liberated with the emission of with the transition of atom to the ground state, right? So here also the difference in the energy state is delta E equal to E2 minus E1. Next topic is expression for energy density using Einstein's coefficient. Now let us consider two energy states E1 and E2 of a system of atoms. Say E2 is greater than E1. Let there be N1 number of atoms with energy E1 and N2 number of atoms with energy E2. So N1 and N2 are nothing but the number density at E1 and at energy levels E1 and E2 respectively. Energy density is nothing but, number density is nothing but number of atoms per unit time per unit volume. That is the definition for number density. Now for this system, So I said there is already some number of atoms which are in the E2 state, some of the atoms which are in the ground state. Such a system we have considered. Now radiation with a continuous spectrum of frequency may be incident on the system. Let there be a radiation of frequency nu such that nu equal to E2 minus E1 by H, and let U nu, that will be the energy density of radiation of frequency nu, then U nu du nu will be the energy density of radiation whose frequency lies in the range of nu and nu plus d nu. So please remember, U nu is the energy density of radiation in the frequency nu, whereas U nu du nu is the energy density of radiation in the frequency range of nu and nu plus d nu. Alright, so I considered a system in which E1 and E2, two energy levels, there are N1 and N2 number of atoms are present. Such a system I have considered in which a continuous spectrum of frequencies which is made to incident on the system. So now we can expect the three different type of the processes, namely the induced absorption, spontaneous emission and stimulated emissions. Why? Because radiation is falling onto the system. System consists of the matter, whereas the continuous spectrum of frequency, that is nothing but the radiation. So radiation and matter interaction is possible. As a result, three different processes are possible. So let us see what are the induced absorptions in this particular case. The number of I already explained about the induced absorption. So I am not going to talk once again the induced absorptions. So the number of induced absorptions per unit time, per unit volume is called the rate of absorptions or rate of induced absorptions. The rate of absorption, which depends on the two parameter, that is the number density of the lower energy state, that is N1, and the energy density U nu. So please remember, rate of absorption is depends upon the two parameter. It is the number density of the lower energy state. Why? Because we are talking about the atoms which are present in the ground state. They have to excite. That is why we are concentrating on the number density at the ground state or the lower energy state. And also what is the amount of the radiation which is falling onto the system, that is also important. As a result, U nu comes into picture. Alright, N1 and U nu are the two parameters on which rate of absorption depends. So now I can write rate of absorption is directly proportional to N1 U nu. If I remove the proportionality sign, one constant will come, that is B12 N1 U nu, where B12 is nothing but the Einstein's coefficient of induced absorption, and 1,2 represents a transition from lower state to higher state. Spontaneous emission, and you know that spontaneous emission is the voluntarily transition from atom in a higher energy state to the lower energy state. Okay, that process is nothing but spontaneous emission. Now number of such spontaneous emission per unit time, per unit volume is called rate of spontaneous emissions. I repeat, the number of the spontaneous emissions per unit time, per unit volume is called rate of spontaneous emission. And this rate of spontaneous emission depends only on the number density in the higher energy state, that is E2 state. Therefore, it depends on N2. Why? Because there is no role of incident radiations, nothing to do with the incident radiation in this process. Only the number density in the higher energy state, they will voluntarily come back to the ground state. Therefore, number density in the higher energy state is matters. I can write the rate of spontaneous emission is proportional to N2. Therefore, rate of spontaneous emission is equal to A21 into N2, where A21 is Einstein's coefficient of spontaneous emission. 21 represents the transition from higher energy state to lower energy state. Next one, the stimulated emission. Now the system requires an external photon of appropriate frequency, that is nu equal to E2 minus E1 by H, to stimulate an atom for the corresponding downward transition, and thereby causing an emission of stimulated photons. The energy density U nu has a role to play in this case. So which means it is quite obvious, we know the definition of the stimulated emission, which means atom which is already in the higher energy state, which will undergo downward transition with the aid of external agency, maybe U nu, that is the external agency or the energy which we have supplied to undergo the downward transition. Okay, therefore let one of the photon in that U nu, that is H nu, that energy is given so that the photon undergo downward transition, the two photons will be liberated upon the transition. So this process is called the stimulated emission. Now number of such stimulated emissions per unit time per unit volume is called the rate of stimulated emission, and this stimulated emission, in the sense the rate of stimulated emission, which depends upon the two parameters. One is the number density in the higher energy state and also the incident radiation, that is nothing but U nu. Why it is N2? N2 because we are talking about the transition from higher energy state to lower energy state in case of stimulated emission. Therefore the number density in the higher energy state is matters, and also the incident radiation that is required for the stimulation of photons. Alright, so the rate of stimulated emission is proportional to N2 U nu, or rate of stimulated emission equal to, remove the proportionality sign, B21 N2 U nu, where B21 is nothing but the Einstein's coefficient for stimulated emission. Alright, and 21 represents again the downward transition from E2 level to E1 level. Now let the thermal equilibrium, which means that the total energy of the system remains unchanged in spite of the interactions that is taking place between itself and the incident radiation. Now under these conditions, number of photons absorbed by the system per second must be equal to number of photons it emits per second by both means of stimulated emission and spontaneous emission processes. Therefore at thermal equilibrium, the rate of induced absorption is equal to rate of spontaneous emission plus rate of stimulated emission. So at thermal equilibrium, total absorption is equal to total emission. That is what the equation. There are two different emissions, you have to sum up, that must be equal to the induced absorption. So that's what mathematically written. Now we have the data for, or the expressions for rate of absorption, rate of spontaneous emission, rate of stimulated emissions. Just you substitute in this expression, it will become B12 N1 U nu, that is the induced absorption term, is equal to spontaneous emission term is A21 N2 plus B21 N2 U nu. Now in this expression you collect U nu terms, that is one term in the left side, another one is right side. So to take that right hand side term to the left hand side with the negative sign, and common term, that is U nu, it is taken outside the bracket. Remaining is B12 N1 minus B21 N2 close bracket is equal to A21 N2. Therefore U nu equal to B12 N1, sorry, it is U nu equal to A21 N2 divided by B12 N1 minus B21 N2. Alright, now we have to do the rearrangement such a way that we need to get B21 into N2, that term should be unity. So what I can do is, I will divide numerator as well as the denominator by the term B21 N2. I repeat, B21 N2. This term I have to take in for the division, either numerator as well as the denominator. Alright. Now if you do so, u nu will become A21 divided by B21 and N2 will be cancels out. That's a numerator term. So I have taken outside the bracket and therefore 1 by second term B12 by N1 divided by B21 N2. That's a second term minus B21 N2 divided by B21 N2. That will become 1. So the reduced equation will be like this. Okay. Now we have to replace this N1 by N2. So in order to replace the ratio of N1 by N2, that's nothing but the ratio of the number density in the ground state and higher energy state. So we have a Boltzmann's law, and it says that the N1 N2 is equal to N1 into e power minus E2 minus E1 divided by KT, or simply you can write N1 into e power minus h nu by KT, where E2 minus E1 is nothing but delta E, that is nothing but h nu. Alright. But we have that N1 by N2. N1 by N2 will become, it is e power h nu by KT. I hope it is clear. N2 is equal to N1. N2 by N1 is equal to e power minus h nu by KT, or reciprocal of that, that is N1 by N2 is equal to e power minus will be eliminated there because you are taking reciprocal, e power h nu by KT. So now you just substitute N1 by N2 is equal to e power h nu by KT in the previous expression, that is u nu expression. Therefore u nu becomes, u nu is nothing but the energy density in the frequency of nu. Okay, is equal to A21 by B21 open bracket 1 by B12 by B21 e power h nu by KT minus 1. Alright. So this is equation number 6 as I shown in the slide. Now let us compare this expression with Planck's law of radiation, that is u nu equal to 8 pi h nu cube by c cube open bracket 1 by e power h nu by KT minus 1 close bracket, equation number 7. Please think of, this is the one equations which we have discussed under quantum mechanics. So now comparing equation number 6 and 7, you can write A21 by B21 is nothing but 8 pi h nu cube by c cube, and B12 by B21 is 1. So in other words, B12 is equal to B21. So which implies that the probability of induced absorption is equal to the probability of stimulated emission. Because of this identity, these subscripts that can be dropped, and the A21 and B21 can be simply represented as A and B. Therefore the equation number 6 can be represented as u nu equal to A by B into open bracket h nu by KT, e power h nu by KT minus 1 close bracket. So this is the expression for energy density. So please remember, this is one of the very important expression. Next topic is condition for laser action. So in order to explain the lasing conditions, there are two important points. One is the population inversion and metastable state. These are the must condition to achieve the lasing action. So let us see what is the population inversion. Population inversion is the state of a system at which the population of the particular higher energy state is more than that of the specified lower energy state. Because normal conditions, the population inversion is not achieved. In the sense, in a real physical system, the population inversion condition does not exist under normal conditions. However, it is possible to achieve the population inversion condition in certain systems which possesses a special metastable state. So metastable state slightly differs from any ordinary excited state in the certain manner. Now let us see what is a metastable state. I hope it is very clear what is a population inversion. In order to achieve the population inversion, it is necessary to pump the atom from ground state to higher energy state, that means the metastable state. In the metastable state, if the number density is more than the ground state, then the population inversion is achieved. That is what the condition of lasing action, that in the sense the first condition to achieve the lasing action. The second condition, the existence of the metastable state. Now, by providing energy, if an atom is made to go to one of its excited state, it stays there over a very short interval of time, say not exceeding 10 power minus 8 seconds, and then returns to one of the lower energy state. Now, if this lower energy state is happen to be a metastable state, then the atom stays in this state for a relatively longer time durations, which is of the order of 10 power minus 3 to minus 2 seconds. Please remember, lifetime of atoms in the metastable state is 10 power minus 3 to minus 2 seconds, whereas lifetime of the atom in the higher energy state is 10 power minus 8 seconds. So, lifetime of the atom in the metastable state is relatively longer in compared to the higher energy state. So, this property helps in achieving the population inversion in the population inversion. Alright, metastable state. Now, consider three energy levels, say E1, E2 and E3 of a quantum system, which are such that E3 is greater than E2, E2 is greater than E1. Let E2 be a metastable state and the atom be excited from E1 to E3 by the supply of the appropriate energy from the external source. So, from the state E3, the atoms undergo spontaneous downward transitions to E1 and E2 states. This process is rapid. In spite of the new arrival of atoms, the population of E1 level cannot increase because ongoing excitation of atoms to higher energy levels. But since E2 is a metastable state, those atoms which get into that state that can stay over a longer durations, because of which population of E2 state increases steadily. Under this condition, a stage will be reached wherein population of E2 state takes over that of E1. This is known as population inversions. So, it is quite easy. Transition from E1 to E3, that is a fast process. Again, de-excitation from E3 to E2, it is also a fast process. Now, the lifetime of atom in the E2 state is very long. Therefore, de-excitation from here to here is a slow process. So, after some times, the number density in the E2 stage will be more than the ground state. So, once this stage is reached, the population inversion is achieved. So, this is the condition for lasing action. Requisites of laser system. So, there are three different requisites of laser system: an excitation source for pumping action, an active medium which supports population inversion, and a laser cavity. The excitation source provides energy in an appropriate form for pumping the atoms to higher energy levels. The energy input may be in the form of light energy. This kind of pumping is called optical pumping. Please remember, optical pumping in the sense energy supplied in terms of light source, which is made use of in the construction of ruby laser. If the pumping is achieved by electrical energy, then that pumping is called electrical pumping. Helium neon laser, it will make use of electrical pumping. Now second part is that is active medium. It is a part of the input energy which is absorbed by the active medium, in which the population inversion occurs at a certain stage. Following this, the stage medium attains the capability of issuing the laser light. A part of the input energy is absorbed by this active medium, in which population inversion occurs at a certain stage. Following this, stage in the medium attains a capability to issue the laser light. So that's a second active medium. So why active medium is required? All the things are happening at the active medium, because once the population inversion is achieved, that's because of pumping. All these things are happening at the active medium. Next is the laser system or laser cavity. A laser cavity consists of an active medium bounded between the two mirrors. The mirrors reflect the photons to and fro through the active medium. A photon moving in a particular direction represents a light which moves in the same direction. Thus, the two mirrors along with the active medium which form a laser cavity. Inside the laser cavity, two types of waves exist. One type of wave comprises of which moves to the right, and the other one to the left, which means one wave in the one direction, the other wave in the opposite directions. That is the meaning of left side and right side. The two waves interfere constructively if there is no phase difference between these waves, but their interference becomes destructive if there is a phase difference. So in order to sustain a light inside the active medium or the laser cavity, there must be a zero phase difference between the light waves. So in order to arrange the constructive interference inside the laser cavity, the distance L between the two mirrors should be such that the cavity should support an integral multiple of half wavelength. That means L is equal to lambda by 2. L equal to lambda by 2 into m. That I said it's a integral multiple. So m into lambda by 2. So it's shown in the slide. It is L is equal to m into lambda by 2. Alright, where m is an integer, it's greater than 0, and lambda is the wavelength of the laser light inside the material of the active medium. Now from this relation, we can evaluate the wavelength of the laser light which is produced in the active medium or the laser cavity. Alright, lambda equal to 2L by m. So please remember this expression. We can solve one or two problems based on this. The first problem, find the number of modes of standing waves and their frequency separation in the resonant cavity of length 1 meter of helium neon laser operating at wavelength 632.8 nanometer. Given L equal to 1 meter. That means the length of the laser cavity is 1 meter and wavelength is 632.8 10 power minus 9 meters. Number of modes m is equal to how much, and also frequency separation nu n minus 1 is how much. So for a laser cavity, just now we have seen the L is equal to m into lambda by 2. So condition for getting the constructive interference inside the laser cavity, the length of the two mirrors that should be adjusted such that you should get integral multiple of half wavelength. Therefore, L equal to m into lambda by 2. So, lambda equal to 2L by m, or we need the number of modes of the which are formed inside the laser cavity. Therefore, m is equal to 2L by lambda. So, since L is equal to 1 meter and lambda is this thing, straight away you can substitute and the modes can be evaluated. It is 3.1 into 10 power 6. This many number of modes are formed inside the laser cavity. And the second part, that is a frequency separation. For a light wave, the lambda equal to c by nu. Now the first expression we have called the expression number 1, that lambda equal to 2L by m. Now from the equation number 1 and 2, both are lambdas, therefore I can equate c by nu equal to 2L by m, or nu equal to 2L by m into c, where m is an integer. Alright. Now if n minus 1 and n are the two successive integer values that m can have, for which the corresponding frequency is nu n minus 1 and nu n, then nu n can be written as nc by 2L, and nu n minus 1 can be written as n minus 1c divided by 2L. Now frequency separation is nu n minus 1, that is equal to that nc by 2L and n minus nc by 2L, that will cancel each other. Remaining is only c by 2L. C is the speed of light in vacuum, and 2 into L, that will be something like 1.5 into 10 power 8 Hertz. A medium in the, that's the second problem, a medium in at a temperature 300 Kelvin has two energy levels, wavelength separation of 1 micrometer. Find the ratio of population densities of the upper and lower levels. So in this problem you are supposed to determine the ratio of the number densities from higher energy state to the lower energy state, that is n2 by n1 is how much, and temperature is given, that is 300 Kelvin. Also lambda, wavelength separation, is given, that is 1 micrometer, 1 into 10 power minus 6 meter. Alright. Now, to solve this particular problem, let me think of the Boltzmann's equations or the Boltzmann law. It will gives n2 by n1 equal to e power minus delta E by kt, or e power minus h nu, or h nu by kt, or nu is nothing but c by lambda. So you can write n2 by n1 as e power minus hc by lambda kt. Why I have written nu as c by lambda? Because lambda is given, nu is not given in this problem. I substituted nu is equal to c by lambda. Alright, so n2 by n1 is equal to e power minus open bracket hc by k into 1 by lambda kt. Hc by k, all these are constant factors. Therefore, I can substitute this constant, h is Planck's constant, c is the speed of light, and k is the Boltzmann factor. So value of the Boltzmann factor is 1.38 into 10 power minus 23, and h is Planck's constant 6.625 into 10 power minus 34, and c is 3 into 10 power 8. If you substitute these things, the constant will be evaluated. It will be 0.014413 divided by lambda t with the negative sign. Now lambda and t is a given parameter. I just substitute. If you do that, you will get e power minus 48.043. That's equal to 1.365 into 10 power minus 21. So that is the answer for the problem. So in other words, if you want to n1 by n2, you can just take the reciprocal of this answer. So that will give the ratio of number density in the ground state to the higher energy state, if you take the reciprocal of this. Next topic is the 3-level laser system. So there are 3-level and 4-level laser systems. So in 3-level laser system, let me consider one energy level diagram, say E1, E2, E3. So condition is E3 is higher than E2, E2 is greater than E1. So pumping can be taking place from ground state to the higher energy state. Now E1 is the ground state and E2 and E3 are the excited state, and E2 is the metastable state. And E3 with the short lifetime, transition probability from the level E1 to E3 is very high. And from E3, atoms undergo rapid decay to the level E2. Thus, population inversion is achieved between E2 to E1. Very high pump power required here because the terminal level of the laser transition is the ground state. Thus, efficiency is lower. So, Ruby laser makes use of a 3-level laser system. This is just for your information. Similarly, the 4-level laser system, this is how the energy level 4-level laser system, E1, E2, E3, E4. So let me give some informations, a glimpse of this energy level diagram of 4-level laser system. E1 is the ground state energy level, E2, E3 and E4 are the excited states. Here E3 is the metastable state, while E2 and E4 have the short lifetimes. Hence, population inversion is achieved between E2 and E3. Here population inversion can easily achieved with the lower pumping requirements. That's all the difference in the 3-level laser system, where we need very high pumping requirements, but here easily the pumping achievements can be done. Thus the efficiency is greater here. The helium neon laser make use of the 4-level laser system. Next is construction and working of carbon dioxide laser. So carbon dioxide laser belonging to the class of the molecular gas lasers. It's a gas laser. Chandrakumar N. Patel designed this carbon dioxide laser in the year 1964. That's at Bell Laboratories, US. Its efficiency is very high and widely used for the industrial drilling, cutting and welding, and also in medical surgery, especially in cosmetic aspects. The carbon dioxide laser is the 4-level molecular laser which operates at 10.6 micrometer in a far infrared region. It is capable of generating very high power of several kilowatts at relatively high efficiency of 40%. It is the most widely used laser in the communication, weaponry and laser fusion. Next topic is the fundamental modes of vibration in a carbon dioxide molecule. So normally these carbon dioxide molecules existing in the 3 different modes of vibrations. The first one, 3 fundamental modes of vibrations of the carbon dioxide molecule are symmetric stretching mode, asymmetric stretching mode and bending mode. These are the 3 different modes of vibrations of the carbon dioxide molecules. The first one, that is symmetric stretching mode. In this mode, the carbon atom is stationary and oxygen atoms oscillate simultaneously to and fro along the molecular axis. So please remember, in this type of mode of vibration, the carbon dioxide molecule is stationary, whereas 2 oxygen atoms either side, they will oscillate simultaneously to and fro along the molecular axis. So molecular axis of that particular carbon dioxide molecule. Alright. So one is stationary, other 2 are oscillating. Next one is asymmetric stretching mode. In this mode, both oxygen atoms move in one direction and the carbon atom moves in the opposite direction along the molecular axis. So here it is not in the same direction. So both are vibrating here, both oxygen as well as the carbon atom in one direction, and carbon is in the opposite directions along the molecular axis. In the previous one, the carbon is fixed at the one particular position, whereas the oxygen molecules are oscillating or vibrating simultaneously. Here in this case, both carbon as well as the oxygen molecules are vibrating in a direction opposite to each other along the molecular axis. The bending mode. The oxygen atom and the carbon atom move perpendicular to the molecular axis. So you can see the picture here. Both of them are oscillating, but in a perpendicular to molecular axis, so that it will balance us. Alright. The internal vibration of the carbon dioxide molecule are the linear combination of the above three modes of vibrations. Normally, this symmetric mode of vibration that will be available in the 100 state energy, or the energy state of this mode of vibration is 100, and asymmetric mode of vibration, their energy state is 001 state, whereas bending mode of vibration is 010 state, and their higher energy states are 020, etc. So before going to the construction and working of the carbon dioxide molecule, or the carbon dioxide laser, in fact, let us understand the collision of first kind and collision of second kind. The collision of first kind is the collision between, that is the collision taking place between an energetic electron and an atom in the ground state. So it's an interaction between energetic electron and an atom which is in the ground state. As a result, a part of the energy is taken by the electron and is transferred to the atom, and the atom moves to the higher energy state. This process is called the collision of first kind. So here atom in the ground state absorbs the energy, that's a part of energy from the electron. Therefore atom excites to the higher energy state, and this state of system is called the collision of first kind. Okay, mathematically we can write the E1, that's the energy of the electron, plus the atom in the ground state A, is equal to E2, that is the energy of the electron after the process, plus A star is the atom is in the excited state. Alright, the collision of second kind. Here it's quite interesting because there are two dissimilar atoms. The collision between them. Let me tell, the collision occurs between the atoms in a metastable state and the another atom of different element in the ground state. Now these two atoms are different. One is in the metastable state, another one is ground state. So in this kind of collision that occurs between an excited atom in the metastable state and the another atom of different element in the ground state, provided the later atom as an allowed excited energy state whose energy is same or the at least approximately the same as that of the metastable state for the former atom, which means the atom which is in the ground state and atom which is in the metastable state, when it goes to the higher energy state, their energy at least to be equal, then only the transition is possible. In such a collision, the energy transfer takes place from atom in the metastable state to the other atom which is in the ground state. As a result, the atom in the metastable state drops to the ground state, whereas the other atom that rises to the excited state. This process can be represented as the A star, that is atom in the higher energy state, interacts with the atom in the ground state. Two dissimilar type of atoms, please remember, is equal to that excited atom that will come to ground state and the other atom which is in the ground state, it will go to the higher energy state. The condition is the two dissimilar atom, one is in the ground state, another one is metastable state. When this ground state atom goes to the higher energy state, their energy, metastable state energy and higher energy states of the same order, then only the transition is possible. And this will help to understand the construction and working of carbon dioxide laser. Sorry. So this is the schematic diagram of construction of the CO2 laser. A CO2 laser consists of a discharge tube of 2.5 centimeter. That's a 2.5 centimeter in diameter and 5 meters in length. The tube is water cooled and is filled with the mixture of carbon dioxide, nitrogen and helium gases in the ratio of 1:2:3. Sometimes traces of hydrogen or water vapor, in fact, it is added. This is why, because during discharge some of the carbon dioxide molecules break into carbon monoxide and oxygen. The hydrogen or water vapor additives help to reoxidize the carbon monoxide into carbon dioxide. And also the pressure inside the tube is approximately 6 to 17 torr. The two optically plane mirrors are fixed on either side of the tube, normal to its axis, as shown in the figure. You can see here. Alright. One of the mirrors is fully silvered and can reflect all the incident light. That means 100% reflectivity, whereas the silvering of the others is slightly less, so that at least 1% of the incident light beam could be trapped by the transmissions. That is the reason why one is 100%, another one is 99% reflectivity. That 1% is which will help to tap the transmissions, so that light comes out from that. And Brewster's window also used, that because Brewster angle windows are prepared to give the polarizer light sources in the laser system. Next one, the working of CO2 laser. So when it comes to the working of CO2 laser, a suitable voltage is applied across the two electrodes. A glow discharge of the gases is initiated in the tube. During discharge, many electrons are rendered free from the gas electrodes, gas molecules or the atoms. These free electrons accelerate towards the positive electrodes, at which time they begin to collide with the nitrogen as well as the oxygen molecules in their path. So liberated electrons will try to collide with the nitrogen and oxygen molecules in their path. The collision belongs to the class of collision of first kind. So I have explained about the collision of first kind. Atom which is in the ground state, where an electron collides with that. A part of the energy will be absorbed by these atoms. So nitrogen or oxygen, whatever it is. Alright. The collision belong to the class of the first kind now, wherein the nitrogen molecules are raised to be first vibrational level. So which is happen to be a metastable state. That's why the particularly nitrogen is chosen for this particular laser. So this their energy in the metastable state and the energy of the carbon dioxide molecule in the higher energy state, that will match. Therefore, particularly or intentionally, we have chosen nitrogen as one of the element in the discharge tube. Now likewise, many CO2 molecules will also be raised to their 001 energy state, which is not a metastable state for carbon dioxide molecule. So nitrogen molecules, this process can be represented as. So no doubt, both nitrogen as well as the carbon dioxide molecules, they will take the energy from these free electrons which are accelerated towards the potential or the positive potential. Alright. So by the time both of them are excited, but nitrogen excitation level is happen to be a metastable state, whereas the carbon dioxide excitation is not a metastable state. Alright, now the expression for excitation of nitrogen is written as E1 plus N2 is equal to E2 plus N2 star. N2 star is the atom in the metastable state and N1 is the nitrogen atom in the ground, N2 in the nitrogen atom in the ground state. E1 and E2 are the energy of the electron before and after the process. Now you can see the energy level diagram here. Now for carbon dioxide gas, it is so happen that there is a close coincidence in the energy of its 001 state with the vibrational levels 1. The nitrogen collides with the carbon dioxide molecules in the ground state. Because of this, matching of the energy level takes place. As a result, resonant energy transfer takes place from nitrogen to molecule. So this is nothing but the collision of second kind. Now atom in the ground state and the nitrogen atom in the metastable state. Okay. So when it comes to the higher energy state, the carbon dioxide molecule, their energy is approximately equal. So there is a possibility of the transition between the nitrogen and carbon dioxide molecules. One is in the ground state, another one is in the metastable state. So as a result, nitrogen will come back to the ground state and carbon dioxide will elevate it to the higher energy state. So that's a collision of second kind. The equation can be written as N2 star plus CO2 is equal to N2 plus CO2 star. So it's quite obvious. Star represents that particular atom which is in the excited state or higher energy state, and CO2 or N2 simply I have mentioned in the equation, which is in the ground state. Now there is an efficient transfer of energy between nitrogen in the excited level and carbon dioxide in the excited level. There is a resonant energy transfer. You can see in the energy level diagram as well here. I put an arrow mark. Now population inversion is created between the energy level E5 and E4, and also between E5 and E3, E5 and E4, and also E5 and E3. So the transition from E5 to E4 produces a radiation of the wavelength 10.6 micrometer, and from the level E5 to E3 produces a radiation of wavelength 9.6 micrometer, both lying in the far infrared region. The other transition from E3 to E2 and E2 to E1 is accomplished through inelastic collision with the helium atoms. The helium atom helps to depopulate the lower energy levels. Also, due to the high thermal conductivity of helium, the heat is conducted away from the laser cavity. I will stop here. Thank you.